Okay, Ian, you can share whatever you want and I will introduce in the meantime. So Ian MacCormack is a graduate student at the University of Chicago and research consultant for Aliro Quantum Technologies. His research interests are the intersection of condensed matter physics, quantum information theory, and quantum computing. With previous work focusing on entanglement in many-body quantum systems, he has recently expanded his focus to include the developments and implementation of NISQ algorithms. So welcome Ian, and he will present the branching quantum convolutional neural network. Wherever you're ready.
Thank you, Alba, and thank you everyone for having me here. I'm Ian. I'm going to be presenting some work that I did with some folks at Aliro Quantum Technologies as well as at Harvard from this paper here. We're going to be introducing a sort of new sort of variational quantum ansatz called the branching quantum convolutional neural network. So first, just I think most people in this audience are familiar with the hybrid quantum classical variational paradigm, but just to go through it, in this sort of algorithm, we have some parameterized quantum circuit, usually some large unitary operator with some set of input parameters that we use to prepare a state. We perform measurements, which are then fed into a classical computer, where we evaluate a cost function. We update parameters accordingly in order to minimize the cost function, and we feed these updated parameters back into the quantum circuit. And we repeat this iteratively, as Tobias described in his talk, until we converge to some optimum of the cost function, and we prepare a state, the state we desire, or some state very close to it. And of course, this serves as sort of a promising early route to a sort of quantum advantage, and there are applications for condensed matter physics. We're interested in preparing ground states of many-body, exotic phases of matter, quantum chemistry, studying different molecules, solving complicated graph problems, and then doing classical tasks like image recognition and other machine learning tasks. And as we go, as NISQ devices, noisy intermediate skill devices go from just a handful of qubits to approaching 100, which is not too far off. We're going to have circuits that can perform operations that are beyond the capability of any classical computer. And so this presents some opportunity for early demonstrations of quantum advantage. Now, the first step to performing a variational quantum algorithm is to pick an ansatz, and there's some intuition and some sort of art that goes into this. You need to pick an ansatz that suits your problem well. Here we're going to be focusing on machine learning tasks, so we can look to successful machine learning algorithms to inspire the structure of our quantum ansatzes. And a recently proposed and successful quantum ansatz is the quantum convolutional neural network introduced by Kong, Choi, and Lukin back in 2018. And it takes the basic structure of convolutional neural networks, which have been highly successful in image classification and related tasks, and translates it into a quantum setting where we input a state into our circuit. We have a convolutional layer consisting of multi-qubit entangling unitaries with parameters that we optimize. That there's then a pooling layer where we measure or equivalently do controlled U operations, and we discard some fraction of the qubits. The remaining qubits then go on to another convolutional layer. This pattern is repeated until we end up with a small number of qubits, and then we measure one or several of the qubits designated as the classification qubits to classify the input state. And using some training data consisting of input states and associated classifications, we train the parameters of the circuit to recognize those classifications. And they demonstrate in this paper this is quite effective at quantum phase recognition, and there have been works on it since that have used it to perform other tasks. So we want to basically take this basic structure and add one sort of crucial new ingredient. That ingredient is a mid-circuit measurement. Until recently, it's been pretty difficult, and hasn't really been possible to perform measurements on quantum devices in the middle of a circuit and then maintain sufficient coherence to subsequently apply more gates, especially gates that depend on the measurement outcomes of these mid-circuit measurements. But there are a few devices now that offer this, in particular the Honeywell trapped ion device, and I think the Alpine Quantum Technologies trapped ion device in Austria. And maybe there are more that I'm not aware of, but I know that those two offer this capability. And so it's interesting to ask how we can incorporate this new capability into a variational ansatz. And so here we introduce the bQCNN, or branching quantum convolutional neural network, which maintains the same basic structure as QCNN, except at the pooling layers, we don't just do single qubit operations based on local measurement outcomes. We take the aggregate of all of the mid-circuit measurement outcomes, of which there are exponentially many, and we use that to determine which subsequent convolutional layer we apply. That is, if we have 4 qubits that we measure at this intermediate pooling layer, we have up to 16 measurement outcomes. That means we proceed to one of 16 different convolutional layers at the next step, each of which possesses its own trainable parameters. And what this means is that we were able to increase the total parameter count, and therefore in principle increase the expressivity of the circuit without actually increasing the depth of the circuit, because at each shot this is the same thing as a QCNN. But overall we have more parameters. You can think of it as an ensemble of different QCNN circuits. So just to explain this a little more clearly, I'll go to the minimal 4-qubit example where so in this diagram, these blue rectangles are 2-qubit unitaries, generic SU4 gates, which can have up to 15 parameters. These green ones are generic single qubit gates controlled on these qubits here with up to 3 parameters. These are measurements, and this dotted box indicates that everything inside the box depends on the classical information from the measurement outcomes of these mid-circuit measurements. So the standard QCNN is the same image, but without the dotted box. So by just, and as an aside, these blue 2-qubit unitaries can be decomposed, for example, into Mulmer-Sorensen gates for a trapped ion computer like this. If we just then count by hand the number of parameters, the standard QCNN can have up to 66 parameters. So 4 of these 15, we get 60, plus 2 of these 3, we get 66. However, with the bQCNN, we have 3 additional classical branches here, 3 different convolutional layers. That adds another 45 parameters, and we have a total of up to 111 parameters. You can see how this can expand rapidly because the number of different branches increases exponentially with the number of mid-circuit measurement qubits. So if we scale this up to 8 qubits, with the same basic structure, the same depth at each convolutional layer, we can have up to like 2025 parameters with the bQCNN and only 315 with the standard QCNN. And if you do some simple scaling analysis, you see that the number of parameters actually grows like this, where n is the number of qubits and p is the factor by which we divide the number of qubits at each pooling layer. So here p is 2. Now, of course, this is not scalable for a sufficiently large system. If we go to 16 qubits, we get something like 500,000 parameters, which is too many. But that's the maximum. You can always reduce the branching structure and reduce the number of branches to still take advantage of some branching and increase parameter count without having this sort of untenable number of parameters. Whereas meanwhile, standard bQCNN, the number of parameters goes like n log n. So this offers the potential to have much more trainable parameters without increasing gate depth, which is important in the NISQ era, where 2-qubit gates in particular still sort of pose, the error rates still pose sort of a barrier to circuit depth. So to convince ourselves that this is possibly useful, we'll generate some artificial training tasks, things that we know that the bQCNN can do, and then we'll see how the standard QCNN does in comparison and in just the training procedure. So what we do is we generate a complete set of just the binary product states. The first qubit here is the classification qubit. It corresponds to this final measurement here. So we have 8 zeros and 8 ones. And then we feed these product states backwards through the appropriate branch as determined by qubits 2 and 4, and then through the rest of the QCNN. And we generate some complicated arbitrary entangled state. Again, we've used random parameters in here. and the associated class label, which we know a priori from just the first qubit in our product state. And as an aside, for those of you who deal with tensor networks, these states are all Mira, multi-scale entanglement, renormalization, ansatz type states. But it's an ensemble of different Mira type states, whereas QCNN is literally just a backwards Mira circuit. Here we have like a diverse set of different Mira states. Okay, so with our set of artificially generated states and class labels in hand, we can then forget the parameters that we used for our random bQCNN and then reinitialize it. And we can perform a training procedure where we feed our states in, we measure the output qubit to get some classification. We then take these measurement outcomes and we evaluate a cost function. And we update parameters. We use a genetic algorithm in order to deal with the large number of parameters and in the hopes of possibly avoiding barren plateau issues, but perhaps that actually doesn't avoid them, as Tobias alluded to in his talk. But in any case, we use a genetic algorithm, which in each generation updates the parameters and updates the cost function. In order to get the bQCNN to classify the states to a greater degree of accuracy. Now we do the same thing with a QCNN of the same depth, but on the same states that we generated with a bQCNN. So we have one set of training data created by bQCNN, and we compare the performance of a standard QCNN with bQCNN. So here we see 1 minus the mean absolute error, which you can think of as just like the percent correctness of the classification versus the genetic algorithm generation. The blue curve here is the bQCNN with 111 parameters, and the orange curve here is QCNN on the same set of data. We can see that early on the bQCNN begins to exceed the performance of QCNN, and eventually there's quite a difference between the two. bQCNN gets up to 90% correct, which isn't that surprising because in principle, if we let the optimization run for an exponentially a very, very long time, we could classify it perfectly. But in a reasonable amount of time, we get to 90% classification correctness, whereas QCNN only gets up to about 82%. And then I think this disparity would grow as the system size grows. And in any case, the performance of the QCNN is always a lower bound on bQCNN because a bQCNN can just be reduced to a QCNN by setting all the branches to be equal. So we can always do at least as well as the QCNN does with bQCNN, modulo potential concerns about overfitting, which is a worthwhile question that we haven't addressed here. Okay, so that was a sort of contrived example where we generated some artificial data just to convince ourselves that somewhere out there in the space of all problems, there's one that we can do well. Let's look at a slightly more physical example. So in the original paper by Kong, Choi, and Lukin, they use QCNN to recognize the phase transition between the Z2 cross Z2 cluster state SPT, which is the ground state of this Hamiltonian here, the first term, to recognize the phase transition from that to just a trivial insulator. And they, as training data, they use the ground states of the first two terms in this Hamiltonian for different values of this H, this magnetic field. And above a certain threshold, the phase transition from the SPT to the trivial phase occurs. So we have a set of ground states and associated class labels depending on the phase, and we train the circuit to recognize those. We conjecture that because of the large number of different branches in the bQCNN, that it might perform well on a diverse set of training data. That is, sets of states with multiple parameters. So what we do is, in addition to varying the value of H and finding the ground state of the corresponding Hamiltonian, we vary the value of this G parameter, which is this 3-site perturbation here. So our training data consists of two sets of states, the ground states of the Hamiltonian with G at 0 and H of various values, and the ground state with H at 0 and G at various values. And they both drive the same phase transition, just in different ways. And and we find we have the phase labels that we calculate with some string order parameter. Okay, so now with this training data in hand, let's compare the performance of bQCNN and standard QCNN, just the training and their ability to learn to classify the phases. And again, we compare the sort of correctness, the 1 minus mean absolute error, versus the generation. And the blue curve here is bQCNN, which optimizes quite quickly and sort of plateaus to just shy of about 75% correct, whereas the QCNN is optimized quite a bit more slowly and does not converge to quite the same. There's about a 5% difference there. And again, this is only a 4-qubit, sort of still quite minimal example. But even in this quite small example, there's a noticeable disparity in the performance between bQCNN and QCNN. So at the very least, it's suggestive that there's a type of problem in which bQCNN is well suited. So again, the motivation for taking advantage of these mid-circuit measurements is to try to increase the expressivity of our variational ansatz without incurring greater gate depth, because very quickly the errors from 2-qubit gates especially accumulate and render the end results useless. So just to demonstrate this, we did some simulations with a simple error model. We decompose our 2-qubit gates into Molmar-Sørensen native trapped ion 2-qubit gates. And after each one of the Molmar-Sørensen gates, MS gates, we apply a 2-qubit depolarizing channel. And before each measurement, we apply a bit flip to just represent local measurement error. Now, there are much more complex errors, especially with measurement. There's long-range crosstalk errors that can occur. But for now, we just stick with these two just to get a basic idea of the performance. And we look at some pessimistic error rates to try to compensate for the fact that we're only using this relatively simple error model. Okay, so let me explain clearly what we do. We generate two sets of artificial data. Again, we run bQCNN backwards to generate perfectly classifiable data, and we do the same thing with QCNN. That is, so if we have an error rate of 0 and we feed these states back through bQCNN and QCNN, the probability of an incorrect classification should be 0. As we increase the parameter count, we can see that bQCNN suffers slightly more from an incorrect classification than the equivalent QCNN. Remember, QCNN of the same depth of bQCNN with 4 qubits has 66 versus 111 parameters. bQCNN suffers a little bit more from errors because of these mid-circuit measurements. It's a constant overhead of error. However, if we extend the standard QCNN to have the same number of parameters just by extending the circuit depth as the bQCNN, then all of a sudden we incur a significant amount of gate errors. And these expand, and the difference between these expand as we increase the error rate up to about 2%. Where here I've set the depolarization and the measurement error rate both at up to 2%, starting at 0.25%. And this difference would grow even further with a larger system size with more qubits. So if we're willing to accept this small additional cost from mid-circuit measurement errors, which unlike the gate depth doesn't grow polynomial or exponentially, it's just a small error cost, then we can pack a lot more trainable parameters into an equivalent circuit depth without much error cost. And with that, I suppose I'll just mention a few possible future directions. So here I've only gone through relatively small scale simulations, just 4 qubits as sort of proof of concept. Excuse me. An immediate thing that would be useful would be to do larger scale simulations with more realistic noise models too. So I think you could probably do this pretty well with matrix product density operators, and you could get to decently large system sizes. And then you could include things like mid-circuit measurement crosstalk error, which is a legitimate concern for this. It would also be interesting to investigate the more general class of problems that bQCNN is well suited for, if there is a general class of problems and it's not just some set of measure zero. My intuition says that this sort of diverse training data with this multi-parameter training data seems to agree well with the idea of having multiple branches. So that would be an interesting thing to investigate, especially on a larger circuit. The next thing, the straightforward thing to do would be to run a small bQCNN classifier on a trapped ion device. As we speak, as I said before, the Honeywell device is actually available on Microsoft Azure, and I'm not sure of the cost, but in principle, you can just go ahead and run it on there, and it has the mid-circuit measurement and classical feedback capabilities necessary to run this sort of circuit. The next thing, which is a possible issue, is to investigate barren plateaus. This, as Tobias described it very nicely before, as we increase the number of qubits, the magnitude of our gradient in a gradient-based optimizer sort of vanishes exponentially. And so you can't just naively make a bigger and bigger variational circuit and hope to do better. There's some evidence I've seen that I think standard QCNN does not suffer as greatly from barren plateaus, in that the gradient only vanishes polynomially. Yeah, it would be interesting to see if bQCNN suffers from the barren plateau issue to the same extent as a generic algorithm, because of course having more parameters isn't very useful if you can't actually optimize your cost function. On top of that, I would add the issue of overfitting. We want to make sure we're not just adding more parameters and overfitting. So here I've just demonstrated training tasks. Of course, we need to also investigate its out of sample performance. That's an obvious next step to make sure we're not just simply overfitting. Another thing that could be kind of interesting was to incorporate sort of more elaborate classical mid-circuit processing. Here we make the decision to proceed to one branch or another, purely just on which measurement outcome we get, but you could imagine applying more complicated functions to these measurement outcomes, perhaps training a classical neural network in tandem with the quantum one that we use to form a decision about which branch to go on to. There's an infinite possibility of ways you can pair up classical and quantum neural networks in this way. And then more broadly, it would be very interesting to see how we can generalize other quantum ansatzes to take advantage of mid-circuit measurement and classical feedback, not just for variational algorithms, but for other quantum algorithms too. It seems that now that this capability is out there and there are more platforms that are on their way to offering it, I think IBM is working on it. It seems like it's going to be a very useful ingredient for taking full advantage of NISQ computing power. So I'm curious to see what creative ideas people come up with that incorporate this mid-circuit measurement and classical feedback. And with that, I'd like to thank you. And if you'd like to see more information, check out this archive paper.
Thank you, Ian, for this nice presentation. And we have 5 minutes for questions before we close officially the meeting. So any questions from the people in the audience? You can just unmute yourself if you wish, or raise your hand. If not, I will start. I have a question regarding how big are the simulations that you use to benchmark this idea?
Oh, very small. These are all 4 qubit. And I did, with the noisy simulations, it was a 4 qubit density matrix. So effectively like an 8 qubit simulation. Very small.
Okay, we have a question from Alan. Could you mix and match also convolutional neural networks in your blocks, given that you measure in between? For example, convolutional neural networks in between measurements and the new quantum neural network.
Sorry, what was that?
Could you mix the convolutional neural network, like classical one, convolutional or classical? I don't know what Alan mentioned. Sorry, Alan.
Explain. Let's just imagine that you measure, right, and you have one of the 4 possible outcomes. You already have you already made a classical code in your circuit, barbarically, right? You already accepted a measurement, and now you're going to reinitialize a set of qubits, right? What stops you from predicting the reinitialization with something more sophisticated? Like you could sophisticatedly put a classical neural network with its own parameters.
Right.
and then start the QNN again, right?
Right. I think this is similar to my second to last point in the outlook slide, where we use the measurement outcome. The classical information we get from the mid-circuit measurement, we use in some more elaborate decision-making process, perhaps with some classical neural network.
So it's the same. Okay, sorry, I missed that point as you were going for that. Okay, good.
Yeah, that's certainly very interesting.
Any other questions? Okay, I have another one, which is, this reminds me the branching mirror approximate. I mean, it has nothing to do with that, because I understand that you don't apply that to simulate. Well, you can simulate actually all these circuits. So, and branching mirror is used to study entanglement that violates the volume law and all this stuff. So I wonder if you can use this approach also to simulate all these systems that are not efficiently to obtain classically with the branching mirror or with the mirror.
Right. In hindsight, I probably maybe shouldn't have called it branching quantum convolutional neural networks, because standard QCNN is basically equivalent to Mira, but this is not equivalent to branching Mira. I did check that. Okay. Branching Mira, standard Mira is useful for critical systems with volume, with logarithmic entanglement entropy growth up to that. And branching Mira, you can have like polynomial or even volume law entanglement in your system. Mm-hmm. But this, this is not equivalent to a branching Mira state. It's better thought of as an ensemble of standard Mira states. So they're still, they still have logarithmic entanglement, but there's just a greater diversity of them within a single a single bQCNN is just a set of Mira states.
Okay. Thanks for the clarification.
Yeah.
So, okay. So I think that maybe we can just close the meeting. Thank you everyone for coming, and especially to the speakers, Ian and Toby. And the ones that, if you want to stay a little bit longer to continue discussions about these works or anything that you want to discuss with us and with the speakers, you are welcome to stay a little bit longer.
So one final remark for people watching this on YouTube. We include chat history in the links under the recording, and Tobias answered a couple of questions in the chat, so you can check this out if you're interested. Yeah, thank you very much and have a nice day.